Name is Ehsan Ghassemali. Welcome everyone. Good morning or good day from anywhere you're joining our webinar. We're glad that you're here. I'm from Jönköping University, professor here, and will be the moderator of one of the moderators of this webinar today. The title of this webinar is How to Think or Deal with Scrap-Based Aluminium Alloys with Low CO2 Emissions. It's, as you see, is the webinar number 41 in series of webinars that we have been having in the WebLearn project. WebLearn is a project that has been supported by KK Stiftelsen or Knowledge Foundation in Sweden for 2 years during the COVID period. The project ended actually in 2022, but we have been seeing very fruitful activities in the project and benefits. That's why we're still continuing the activities, although the funding has been stopped. Very glad to have you here. As you see, we have been having a large number of registrants to this webinar, close to 72 registrants from different countries. I counted this morning close to 13 to 15 countries around the world are represented here in the registration list, and many of you have been are joining this webinar. We are very glad to have you with us. As I said, WebLearn is a project that has been running since 2020, and we have been developing webinars related to metal and polymer component manufacturing. Aspects related to sustainability, circularity has been the main focus, but also other aspects in generally manufacturing of components using these two very strategic materials in the industry. These are the moderators of the webinar today. Myself, as I mentioned, Ehsan Ghassemali, and my colleague Madeleine Zetterlind, who will take care of all practicalities for the webinar today behind the scene. But we are not the most important people here. The most important people as organizing this webinar are these three colleagues, as you see on the slide. Dr. Joachim Högström, a research leader at Swerim in Stockholm. Dr. Carl Magnus Lancelot, a technical sales and support manager at Thermocac Software AB in Stockholm, and Professor Anders Jarfors from Department of Materials and Manufacturing, School of Engineering, Jönköping University in Sweden, will run the discussion and present the slides to you related to the topic of the webinar. This is a rough agenda. After my brief introduction, we leave the scene to our great speakers to talk about the topic. There will be three distinct but connected presentations from three speakers. After that, we will start close to 45 minutes. There will be these presentations, after which we start the panel discussion. And we would like all of you to attend to this panel discussion and contribute to the questions and answers, and make sure that it's a dynamic discussion and it's not only one-way presentation from us to you. We hope to end this webinar by 11:30 Central Europe time. Some practicalities about the webinar format. We would appreciate if you turn off your microphone during the presentations, but not during the discussion. Please turn them on during discussion. During the presentations, you're welcome to raise your questions or comments in the chat, and myself and my colleague Madeleine will take care of those and make sure that they are addressed after the presentations are ended. Panel discussion, as we mentioned, is very important part of our webinars. We would like to have our webinars dynamic, and we would like our audience to contribute to the panel discussion. So you're more than welcome to contribute to that and share your ideas. Our webinars are recorded. It is being recorded right now. The recording will be available afterwards to you and colleagues who have, or other people who have registered for our webinars. If you do not want to be shown in the recordings, please turn off your camera, make sure it's off. And what we do not record is the discussions, because we would like everyone to feel free to discuss any ideas. Therefore, we will not record those, but we only record or we will not share the discussion. We will only share the presentations. I think thanks to COVID, we all know how Zoom works, but in case it's your first time using Zoom, or you have forgotten because you have not used it so much, you can find the practicalities and where you can find buttons to click for muting and unmuting your microphone, or turning off or on your camera, and where to find the chat function to send us your ideas or questions. That was from my side. And as I said, I'm very glad to have you all here. We look forward to this webinar. And by this, I leave the floor to my colleague Joachim, who will present his perspective from Sweden. Joachim, the floor is yours.
Thank you. See if I can do this. So, hello everyone. This seminar today is a part or final part of a pre-study, genomförbarhetsstudie, pre-study from within the program Metals and Minerals, sponsored by Vinnova in Sweden.
Joachim, I appreciate if you share your slide or screen.
I do not do that.
Just need to click on share.
I have to leave the presentation mode then, or?
Possibly.
I thought I pushed share.
I think you need to confirm by selecting a screen to share.
Okay.
Okay. I think it's starting.
We practiced before, but
Yeah.
Yes.
Okay.
slideshow. Okay.
Great.
Perfect.
Works. Sorry for this. So this seminar is within this pre-study called Thermodynamic Simulations for the Development of Low Carbon Emission Scrap-Based Aluminium Alloys. And the participating parties was Swedish Aluminium organization with Peter Benson, Thermocalc Software, where Carl Magnus and Yang was participating, Jönköping University with Anders, Esan and Lucia, and from Swerim it was myself and my colleagues Sten Westman and Fang Ting. So the project idea was that we all know that aluminium produced from secondary sources only need a small part of the energy compared to virgin aluminium produced from bauxite ore. And the carbon dioxide emissions are close to zero if we use green energy. And the way to go is to increase the usage of scrap, also in high performance, high pressure die cast and wrought products, the mega and giga castings in automotive industry, for example, and extruded profiles and rolled sheet materials, where it's today mainly virgin metal. And the main challenges to do this is the accumulation of unwanted elements like tramp elements, impurities, non-metallic inclusions, which can have a negative effect on final properties. The largest volumes, though, of available scrap is not the high quality scrap that is well sorted. It's the mixed scrap and alloy scrap. And in the future, already today, the high quality aluminium scrap is expensive. It can be more expensive than virgin metal. So in this situation, thermodynamic calculations and simulations are useful tools to understand and help predict the influence of variations in composition and microstructure and properties. But this is maybe the core of our project idea. It's that the thermodynamic simulation tools, they are dependent on high quality information, phase diagrams, and secondary alloys contain more elements and in larger amounts than the alloys we have used in the past. So we need to develop better data. And our project aimed at to make a gap analysis of available data to understand where do we need to make more experiments. This was one of the most important tasks of the project. Then we also wanted to improve the competence in industry and among researchers in Sweden, and we therefore wanted to produce educational media that can be used for meetings with industry. And the third option was just this, to meet the Swedish aluminium industry, to give seminars and to tell about basic metallurgy and phase diagrams and how these thermodynamic tools can be used. We also wanted to create demonstration cases to exemplify how alloying elements and impurities affect processing parameters and properties. And one final important thing was also to gather a consortium that are interested in working with these issues, improving databases needed for simulations of complex scrap-based aluminium products. And everybody talks about scrap, and we have to use more scrap. And the hard truth is that the scrap is not really available to everything. So that's why we have to make also the low quality scrap available for more high quality products. And to the right, it just shows how much we gain in using secondary resources to produce aluminium. And this is the forecast of aluminium production in million tons. We will see a quite large increase in the amount of aluminium produced due to the automotive electric cars, in automotive transports, and in many areas. And we see that the recycled content, according to this graph, which comes from a presentation of Rabe, it says it's in 2050 we can expect 50% of sources coming from recycled material. So it's really, we have a huge job to do to try to increase the amount of recycled material. And the project deliverables was really to have a review of existing computational tools of thermodynamic simulations. We want to have user cases with examples of how simulations can be used in industry. This will be presented by Thermocalc Software today and Jönköping University. Also, we have a review of competences, skills, and tools in the aluminium industry. And we made several trips to meet industry and to try to make researchers at the research and innovation centers to understand the situation. And now we are here at the final workshop to discuss the results and possibilities. So thank you for I'm ready with my part then. Thank you.
Good.
Great.
Thank you.
Thank you, Joachim. Now, we talked about solid scrap and thermocalc. So now it's time for Carl Magnus to tell us about phase-based prediction for aluminium alloys, the activities we did also during Tall Scrap project.
Thank you, Kim, and thank you, Esan. Let's see here. Can you see my screen okay?
Yes, perfect.
Good. So I've worked together with Dr. Yang, who is our database developer for the aluminum alloys database at Thermocalc. And I also need to acknowledge several of my colleagues, including Bharat Mehta, who's one of our aluminum experts here in my team. So I will first give a quick introduction to Calfa-based software and why we should use Calfa-based software and who should use it, who could benefit from it. And then there are 2 points that are basically the 2 different work packages that we at Thermocalc had during the project. One was to create an educational package that serves as a sort of an overview of different ways that you can apply Thermocalc in the aluminum industry. So I will give you a sort of an overview of these different applications. And then the second package is to identify data gaps for improving the database. And we have identified a couple that we could work on to improve the thermodynamic predictions in the future larger scale project that Kim introduced. All right, so why should we work with computational thermodynamics? And who could benefit from using this kind of predictions? Actually, most of the life cycle in the aluminum for the aluminum alloys. The alloy designer who will prepare the chemistry and make a cast. The component producer who takes this cast and makes it into a shape and heat treats it. The component user who takes this component and puts it in a product. Probably not the end user. The end user would be me who buys a car and drives the car. But also the recycler who will recycle the scrap and then that will go back into the alloy design. And why should we use computational thermodynamics? Well, we can minimize the need for trial and error, experimental trial and error. That can be very costly if you have to turn off production in order to do experimental trials. It's better to be able to make predictions before in order to narrow down the experimental needs. So you can save time. You can save your development time from the drawing board to the final product. And also, as Kim has already introduced, we need to use more recycled aluminum. So in the future sustainable society, we will need to have more innovation for scrap-based aluminum alloys. The current aluminum alloy specifications are not very tolerant to chemical variety, especially the wrought alloy grades. So these can be very sensitive to impurity contents. So it will be important to design new alloy grades that are impurity tolerant. And also design processes to recycle these scrap materials. And now I'll give a bit of an overview of the databases that are the foundation of these predictions that we can make in Thermocalc. So these are CalFAD databases. CalFAD stands for calculation of phase diagrams, and we work with phase-based properties. These properties are evaluated for all phases that can appear in a type of alloy. They are developed using experimental data and also atomistic simulations, and they are described as a function of chemistry, temperature, and to a limited extent also pressure. And the properties are the Gibbs energy, which can be used to derive all kinds of different thermodynamic properties, and also the phase equilibria, so we can calculate phase diagrams, and also atomic mobility, so we can simulate the kinetics of phase transformations, and also some thermophysical properties such as molar volume and the viscosity and the surface tension of the liquid phase, the melt, the thermal conductivity and the electrical resistivity of the alloys. And we're currently working more and more on introducing elastic properties into the databases. With this, we can simulate the microstructure you will have in the alloy. We can simulate processes such as additive manufacturing or casting, and we can evaluate the properties of the resulting materials and evaluate the performance of the materials. So that's just a very brief sort of overview and summary of the predictions we can make with this CalFAD software. So I want to talk, of course, about our aluminum database, and our main developer is Yang. And during this project, we updated this database to version 10 with some improvements that we managed to identify. We have 48 elements. They're all shown here, marked in the periodic table. We have aluminum here, and then we have the major alloying elements are green, and the yellow ones are either minor alloying elements or impurity elements. There are over 300 binary systems assessed in this database, over 100 ternary systems, a couple of quaternary systems, and also over 700 phases described in this database. So for all of these phases, we have all of these properties described as a function of temperature and chemistry. And the properties are the Gibbs energy, molar volume, thermal conductivity, electrical resistivity, and the surface tension and viscosity of the liquid. We have not yet gotten to adding the elastic properties, but that's on the roadmap for the next update of the database, the elastic constants. And so I will give an overview of the different applications we can do currently on cast alloys, wrought alloys, and also I will talk a bit about the future of aluminum and the sustainable aluminum alloys. And all of this different predictions we can make as a function of different chemistry and temperature. So for cast aluminum alloys, of course, we want to be able to simulate the cast microstructure, and we can do that easily either using the Shell-Gulliver equations in the Shell calculations. We can simulate the cast microstructure. We have some dendrites, we have some eutectics, and we have some intermetallic compounds forming, including the segregation profile during the growth of these dendrites as a function of cooling rate. And then we can bring this information into a diffusion simulation to simulate the homogenization of this cast structure. So we can simulate the flattening of these segregation profiles. Here is an example at for 12 hours at 540 degrees Celsius. And also, maybe more important for these alloys, the dissolution time for different detrimental intermetallic compounds, such as Mg2Si phase. And also very important to cast alloys is the hot cracking or hot tearing susceptibility. We have a model in the software for this using there are different kinds of models that you can select, but we can calculate this as a function of different chemistries. In this example, we have a multi-component alloy with many different impurity elements, and we are varying the copper and zirconium content to see how the alloying is lowering the hot cracking susceptibility. And also some important properties to the casting and melt properties. The cast shrinkage, so the increase in density or the decrease of volume during solidification, or the viscosity, for example, here for a couple of different cast alloys. Very important for the behavior of the melt, the flowability and so on. Next, quick overview of applications to wrought aluminum alloys. So wrought aluminum alloys, we do thermomechanical processing, so we can identify processing windows. This example is on alloy 6063, but you can do this on any kind of alloy grade. So here we show the equilibrium phase fractions as a function of temperature, representing the microstructure. You will have at different temperatures, so you can identify some temperature limits. For example, here the solvence temperature for the formation of Mg2Si, which is a problematic intermetallic compound. So this will set a lower temperature limit for a processing window. And then we can have an upper temperature limit where we get melting or incipient melting of the alloy. So we have a processing window here, for example, for extrusion or other types of processing, but also for homogenization treatment. So we also, of course, we can simulate the homogenization treatment of this alloy. And here it's interesting to convert the problematic beta particle into the alpha particle, which is a bit better for the properties. And we simulated this at 550 degrees right here, which is between the beta and the alpha phases right there. And then for wrought alloys, you usually do a precipitation and age hardening treatment at a lower temperature, such as 200 or 180 degrees, and we can simulate this in the precipitation modules here. Now we're looking at a 6005 alloy grade and the precipitation of beta double prime needles. This is a metastable precipitate, and there's a transformation between spherical and needle morphology. So here we look at the number density of the particles as a function of time during the precipitation treatment, and also the mean radius and the aspect ratio of the particle as a function of time. And then when you've done this kind of simulation and you're happy with the results, you can use this to model the hardening of the material. But now these are examples on binary alloys, aluminum zirconium and aluminum scandium. So here we are simulating precipitation of aluminum zirconium precipitates and calculating the Vickers hardness for two different chemistries. And here on the right, this is one of our oldest examples of the yield strength model, where we are simulating the strengthening effect of the aluminum 3 scandium particles as a function of time. And I want to move on to talk a bit about the future aluminum industry and the sustainability with aluminum. So 3D printing is becoming more popular. It's become more popular to try to qualify aluminum alloys for 3D printing. And we have this integrated additive manufacturing module where we can simulate the laser powder bed fusion process using all of these different properties that I have just showcased. So here we have an example of aluminum silicon 10 magnesium alloy. So we can design the printer parameters or design new printable alloys, for example, using the modeled melt pool behavior as a function of different laser power, wavelength, also laser beam shape and beam radius, different scan strategies such as scan speed and hatch spacing and hatch rotation and all that. And we can model all of this and optimize the printing parameters to avoid printing defects such as lack of fusion and keyhole porosity. Moving on a bit towards recycling now, salt fluxes are used commonly to clean the aluminum melt, and we have descriptions in our databases that can help model this. So we can design the salt chemistry for the optimal cleaning of the aluminum melt. Here we have a potassium chloride mixed with magnesium chloride, and we're increasing the proportion of magnesium chloride in the salt flux to look at removing sodium and calcium impurities from the melt. So we can see we will reach a satisfactory value here, while also maintaining the magnesium content in the melt. So we can see that while increasing the magnesium chloride in the flux, we don't add very much magnesium to the aluminum melt. And then looking forwards into the future of scrap-tolerant aluminum alloys, there are several publications out in literature where thermocalc is used to design new types of scrap-tolerant alloys. These are mostly cast alloys, of course, because cast alloys are a bit easier and more tolerant to the impurities. But I wanted to highlight at least two papers here. One is by Pavel Shurkin et al. From 2021, where they looked at an aluminum zinc magnesium alloy. So here is a heat treatment window for the aluminum zinc magnesium alloy. The dashed lines are the curves, the volume fractions of the phases in this alloy. Where we have a treatment window where we have 100% FCC phase. And then adding iron and silicon impurities removes this processing window so that this is no longer processable. And then they made further predictions to design a new high strength and iron silicon tolerant aluminum alloy. And another more recent paper, which is quite nice, by Jon Michael Sanchez et al. From this year. They designed a fully post-consumer scrap-based cast alloy. They had sorted scrap in maybe 6 different categories, different chemistry ranges, basically. And they did a high throughput calculation in thermocalc to screen the properties of 94 different chemistries. And they made these quite interesting diagrams. These are column diagrams showing the volume fractions of all the different phases at different temperatures. Here at 500 degrees and 25 degrees. So at high temperature, you can look at the detrimental phases that will form during the cast, and also homogenization windows. And at low temperatures, you might look at other phases that can be problematic forming at lower temperatures. And they also looked at other important properties such as the density of the alloy. So they made a castable, good strength, fully scrap-based alloy using these tools. And coming back to our work packages, so that was sort of a review of the current status and capabilities with our databases and the tools. And I want to talk a bit more about the next step, the gap analysis, which was mainly performed by my colleague Yang Yang, the database developer here. She's doing the validation work of the database, where she validates the database for many different multi-component alloys, calculated some important properties such as the solidus and the liquidus temperature for a large number of commercial alloys. These are both wrought and cast alloys, but we can see a pretty good agreement here within plus minus 15 degrees for the solidus and liquidus temperature, and we can also see which outliers are here in the predictions, and that can help identify areas where there could be improvements made. But most importantly, in order to improve predictions on multi-component alloys, we need to identify critical ternary systems that are important for these scrap impurities that will contaminate the alloys, for example. And Yang managed to identify quite a few and improve a few of them during the project. One of them is aluminum iron manganese. That was improved for version 10 of the database. There was some deficient data in a certain temperature range where the data points were conflicting, and there might have been contaminations in the data points in the literature. So she managed to make some critical judgment and make an improvement to the description. Aluminum chromium iron was actually not described before because there was limited data available, but now there was new data, and we were able to assess this ternary system and put it in a database, which of course will be very important for predictions using with chromium and iron based intermetallic alloys, intermetallic phases. Another ternary, aluminum copper manganese system. There's very deficient data available from the 60s. So this is a system where we have an opportunity to create new data. If we can create high quality ternary data, we could rule out some inconsistencies in data, the old data, and improve this system. Aluminum copper iron system was also improved during this project. We managed to improve the copper solubility in several aluminum iron based intermetallic phases, which is very important for scrap based alloys. Another ternary, aluminum iron magnesium system. There's no data at all available on this ternary system, which is a bit surprising, or it's just hard to find in the literature. So this is very important to 5000 series alloys. So we hope that we in a future project can be able to generate data on this ternary system. Aluminum magnesium manganese system. This is very important to 3000 series alloys, and there's very old data available in the literature, which is a bit insufficient for a good thermodynamic assessment. So here we have some couple of ternary systems. We have the opportunity to make improvements in this future project that we hope to be able to put together. And what experiments do we need to do? So I want to emphasize that it's most important to generate high quality ternary alloy data, much better than multi-component alloy data. Multi-component alloy data is good for validation of the database and identifying areas of improvement, of course, but high quality ternary alloy data is important to be able to improve the database. So a very cheap method is to make isothermal heat treatments. You define, here's a schematic term.
We lost your sound, Carl Magnus.
And we also have a ternary intermetallic compound here, and we have some two-phase regions with the green tie lines, and also these red triangles are three-phase triangles. So if we can prepare sample chemistries to try and pinpoint them into these two-phase or three-phase regions, we can gather a lot of ternary phase diagram data in a single furnace heat treatment. And we can also put samples for different alloy systems in the same furnace. And then if we do this for a couple of temperatures, 3 or 4 temperatures, then we have gathered a wealth of data that we can use to assess these ternary systems. Combine it with some XRD and maybe EBSD, that will help phase characterization a lot. And also DC or even cheaper DTA analysis, differential thermal analysis, is used to identify phase transformation temperatures. So here we can scan the liquidus projection of a ternary system, so we can get the liquidus and the solidus, and also some solid phase transformation temperatures. We can combine it with XRD if we want to really be certain of the phase characterization there. And maybe a bit more expensive method, but also very useful, calorimetry. We can measure heat capacity and enthalpy of formation of if we find some new ternary compounds. This will generate very important data for the assessments. All right, and that was all that I had to present about our 2 work packages in this project. Thank you all for listening to me, and I hand back over to Esan and Anders.
Perfect. Thank you very much, Carl Magnus. Very interesting insights on thermocalc, and as we know, and as you also briefly mentioned, the capabilities of thermocalc are endless, sounds like, and a lot of potential to use it more, even for scrap material in aluminium. Now it's time for Anders to present his perspective about tall scrap, what we've identified in tall scrap as benefit for the industry. I'm going to share my screen for you, Anders, and
thank you.
Help you running the slides.
Yes, so I hope everybody hears me well now. Well, the task for us was to sort of say identify where you can benefit using thermodynamic computations, and that means that we need to understand the scrap systems a little bit better. We need to understand what the problems are, and I will talk a little bit about how the scrap scene is changing now with electrification and some other elements. I will also mention a little bit about the work that we have been doing and exemplify issues that we can see and how we can so to say, see possible improvements as well. And these are naturally connected to what Carl Magnus also just mentioned when it comes to the gaps with the aluminium, iron, manganese descriptions, aluminium, copper, manganese, aluminium, iron, magnesium, and aluminium, magnesium, manganese systems, of course. So next, please. So going in with scrap-based material, this has been mentioned already today, but what we have is one part is inclusions and issues with inclusions. And the most common problem we have is various oxides that come up. And then we have chlorides and carbides typically being formed. Now, these are often related to the recycling processes, and they are related also to the actual manufacturing and processing operations that you have and how you melt and treat your melts. But these are issues that will increase during the handling and processing of the materials. Now, with the scrap chemistries, you have variations in chemistry. So there are ways that we normally do. So one part is to dilute the scrap. But this is very difficult. So if you have a small variation of a trace element and you need to half that, that means that you need to have 50% dilution. So that is one element to deal with. So trace element can make huge needs of dilution necessary. The other part is the alloying elements. And since the description or what you get in scrap is a little bit more uncertain, so that means maybe being able to accept wider specification is also one part. And all these things with trace element uncertainties and wider specifications that might be necessary means that you get more particles and even more particles, and all these particles affect your properties and your processability. Now, trace elements, as we understand now, is that trace elements, they have a little bit uncertain consequences. Maybe they just act on viscosity, maybe they change surface tension, and that means fillability and pore formation and such are issues. And as Carl Magnus showed also with the heat treatment windows, there is an issue that these windows may disappear with the addition of some copper, for instance, as a trace element. So all these with process window changes and change processing behavior, all these are uncertainties that we need to be able to understand and deal with. And also the product outcome. We've seen that we can predict some mechanical properties. There are also issues in and around the corrosion properties of materials, which are also even more difficult to talk about, because they are not only depending on the material, they also depend on the environment. So these are the general problem that we as an industry face when you try to, so to say, deal with the uncertainties coming from scrap. And this has led to a normal way that you either dilute or you downcycle. So you have a heat, a source and sink paradigm that we've been working with so far. So if you take next, please, Esam. This is a source and sink diagram where you have the scrap source types on the left, where you have 1100, 3000 series, 5000 series, 6000 series, and then your typical cast materials with 319, 356, 380, and 390 being the sources. And at the bottom, you have the zinc alloys. And this is, if you take, for instance, 6000 series, 6061, you can actually produce an 11,000 series material. But what will be limiting there is the copper and silicon content. And that limits then, as you can see for the color, that you can take no more than 10% of this material because it's limited by the copper and silicon. So what you see in this, if you take the wrought materials, the 1000 series materials, often you have magnesium being the limiting element. And if you go down to the source is coming from the cast alloys, making wrought materials is very challenging because you have copper and silicon being the challenges. Now, if you go and see the wrought materials, and we can take the 5000 series, for instance, and then choose to have the 300 series, the cast alloys being the sinks, then you see it's magnesium also being dominant here. But what happens is that because of the cast alloys having a higher tolerance of these materials, you can actually increase the amount of wrought materials being used here. So that means that you go up and you turn more and more towards the green range or the blue range of alloying elements. So this has been, so to say, the forgiving paradigm. And if you talk about the main elements, we can see that one of the more troublesome is the magnesium material we have. And then knowing also that iron is an issue. And if you remember here that aluminium, iron, magnesium was one of the ternary phase diagrams that is an issue. So already at this point, we can say that the insufficient description of the aluminium, iron, manganese system actually hinders us to effectively utilize this, because we have the uncertainties of the iron enrichment being seen in scrap. So managing a good source and sink system is difficult. So the question is now, what is happening with the scrap? Because some of the large volume products we have are coming from the automotive industry. And in tradition, you would have a cast alloy being the end of usage for all the aluminium, and that is essentially the engine block. So you would have the A380 type of alloys for that type of application. Now, what happens then is that if you take next, that there have been some work where you take a shredded car and then you remove as much of the iron that you can have and all the non-metallic impurities that you have, and you end up with the aluminium composition. So what we have here are three different scenarios. So if you take the internal combustion, and these are actually based on experimental data where people have been shredded cars and then separating out for the internal combustion, you can see that the leftmost of these bars, you have just above 5% silicon in the sorba scrap. You can see that you have 0.5% of iron in the sorba scrap, 0.7% copper, 0.3% manganese, 0.75% magnesium, and 0.41% zinc in the scrap that comes out of this shredded material. And this is what you need to work with. Now, this is what comes out as a sorba. But if you look at the cast alloys, they typically have, which is then the downcycling part, they would have maybe 10% silicon. And that means that you need to add silicon in this. And typically, if you take data from our recyclers, you have 20% of the energy that goes into recycling the material and making from the sorba scrap into the cast alloys. 20% of the energy that goes into that is the addition of silicon. The other part you have is that silicon is also a very dirty element when it comes to carbon footprint. So 70% of the carbon footprint in the recycling process is also coming from the silicon addition. So that means that there is a need to rethink your alloying systems and maybe match what is coming out of sorba a little bit better, even if you want to do castings. And this is what we see for mega castings, for instance, that there is a change in that. But the first thing that we need to deal with is what happens when we change to the electric vehicle. So in this study, they had also been shredding electric vehicles. So what you see when you shred the electric vehicles, you do not get 5% silicon anymore in the car, you get 1.3% silicon. So that means downcycling here means that the scrap would increase its carbon footprint, and increase the amount of energy that would needed to be put into the recycling the recycling process if you want to increase the silicon content. Now, the problem in this is also that the combustion engine is disappearing. So that means that zinc will no longer be there. So that means that one needs to rethink the material flow completely. Now, the saving grace here now is that this is the study by Anton Rolset, where we did some scenario planning and looked at what happens if we now add the mega castings, and that means you add the rear floor to the cars or the front or some other elements, battery cases and such. Those alloys do not have a huge amount of silicon. They typically have like 7 or 8% silicon. So the consequence of the rear floor being added and replacing steel components means that the average composition of the scrap coming from Sorba would end up about 3.5% of silicon. And you can see the iron content goes down a little bit because it still used the primary materials for that. And the copper content is a little bit higher compared to what you get from the electric vehicles, but it's still less than what you get from the combustion engines. The manganese content is still in the order of 0.3%. Magnesium is increasing a little bit, and then zinc is even lower here. And this is also one part because zinc is often coming in from the heat exchangers, and that is something which is going to have a separate scrap route because of the freons and such. So if you take the next slide, the conclusion is then that we have a number of alloying elements in the aluminium scrap mix. And if we just look at the electrification, we have less copper, less silicon, but more magnesium. And what we remember now is that magnesium was one of the elements that to a large extent put a limitation. So if we put scrap back into our alloying element cycle into the alloys, that means that it will be even more limiting because you would have an increment in your magnesium content. Now, gigacasting will not really strongly affect that, but we will put some silicon back into the system. And there's a window here now. So if we start using alloys that have less silicon, we can also reduce the carbon footprint. And so this is an interesting concept. So now what we saw from Kim's presentation is that there will be a deficiency of aluminium. And our studies where we looked at a closed recycling in the automotive industry, so you have a closed circuit recycling in the automotive industry. We can go to the next slide. We can see that the deficiencies in 2040 would be in the order of some 20 megatons of aluminium. But there is not really that big a deal between the combustion engines and the electric vehicles and the mega casting scenarios. So this is something that it's about the same level of issues. But the interesting portion is, if you go to the next slide, is what happens with the alloying elements, because the scrap that comes back from the cars will be richer in magnesium than what the automotive industry actually is using. And we can see that silicon around 2037 will be higher. We can see that magnesium will be higher. So one of the abilities that we need to work with is actually to use the scrap as an alloying system, being able to do more complex alloys and returning the scrap into cycle of more qualified alloys. So that's the challenge. So if we go to the next, this you probably recognize as the Gulliver-Scheil calculations, and these are for 6 different alloys, which are slight mix between 3,000 and 4,000 materials. And what comes back as a processing challenge in these are the hot tearing issues, And hot tearing is determined by the lower left corner, and they all look the same in this. Experimentally, they are very different, but if you look at these from a prediction standpoint, they are more or less the same. So there are some issues in predicting the hot tearing issues here. And if you take the next slide, this is an example where we've been calculating the hot tearing index of the materials with function of different compositions. And this is a plot that we've done, and we used thermocalc and the Scheil equations here, and we are working on our own model here in order to produce this. But we've been doing 500,000 of these Scheil calculations here, trying to show how the various elements are, so to say, behaving in this system. So you can get data out of this as a qualitative measure, but there are also issues in actually fitting this to the experimental work as well. So we can take the next slide, please. Now, when it comes to developing strategies, we need to think about what is happening when you do this. And this is an example then from rolling. So we talked about particles. You can see the rolled structure to the left. This is the particle richness. And then you get the microstructures. So what we have is an influence of the homogeneity of the microstructure as a consequence of increased particle content. And then this needs to be rolled or extruded or cast in some way then. So I think that we can go to the next. Now, this is another study that we found during the project here, where you have the links between the cooling rates in the casting process and what happens then when you roll these materials later on. And I think what is important here is to look at the tensile curves. If you take the lower right curve, you can see that the red curve is showing a reasonably high iron content and a manganese content, and it has a significant reduction in properties. But if you go to the upper left, where you have a fast cooling, what you can see there with the fast cooling, you actually get a decent performance even with a high iron content. So that means also understanding the effect of your processing conditions becomes very, very important here in order to be able to produce good materials with both high performance strength and good elongations. So this is really something where we need to work more and understand this better in order to predict how the microstructures are formed and how they change during our processing. So we can go to the next. So the key points of the benefits here that we can see. One part is that we can reduce cost and climate impact by smarter alloying. We can reverse the downcycling and try to start working with upcycling instead. We can be more prepared for the change in scrap supply mix, because we know that what comes back as a Zorba scrap will not be constant in composition. It will reduce in silicon content. And what we need to do is to cast with better care. So that means reduced silicon content, and maybe we can accept higher iron contents. When it comes to the raw materials, it's particles, particles, and particles. We need to keep those under control. And then we need to improve our capability and understanding the combination of rolling and forming together with the casting of these materials. I think that's my last slide, I think. So we can go to the next. Yes. Well, the summary is that scrap supply will change in nature and chemical composition will change. And there are some powerful tools that we will use here. So thank you for this.